Welcome to the session about chaos engineering. Let me quickly introduce myself. My name is Geert from Cruijsen. I work at a company called Geert. We're a bunch of consultants who help, basically software companies build better software by doing several things. Moving them to the cloud, build better software architecture, applying DevOps principles and those kind of things. And I like to combine all those areas. So I like moving teams to the cloud and really use the agility of the cloud to make teams faster. I'm a developer by heart. I call myself a full cycle developer because I believe development is actually something you do from writing some code to actually moving it into production and seeing what it does in production. I don't believe in throwing code over the fence and then someone else will fix the trouble for you when it runs in production. I often go into companies and coach them, and that's my role. As I said, I work for a company called Geert. We have a motto. Our motto is called "Do Epic Shit." We even design T-shirts for that. I have a couple of T-shirts for after the session. If you make any pictures during the session and tweet them to my handle, if you can show me the tweet, I will give you a shirt. So let's get started. Chaos engineering. Anyone here who already does chaos engineering at their company? One? Okay. Well, that's good, and really good that the other ones are not doing it, because, well, that's why I'm here for, right? Giving you an introduction of how you could get started with these kinds of things. But first, why do we need chaos engineering? Well, IT is becoming more and more important in each and every company, right? If you're an IT company, of course, that's for sure. But if you're a bank or something else, almost all companies are software companies nowadays, right? And when your IT fails, you can get into news. Well, last year it was quite over the news that some small bug caused all the trains near Amsterdam to fail for several hours, impacting, well, society. But it can also cost a lot of money. Amazon, for example, well, you know, they're the biggest retailer online. They actually had some downtime during Prime Day, which is their Amazon discount day where you can get lots of discounts. And they sell a lot of products during that day. Well, they lost about 100 million because they had some downtime during that day. Well, this is something chaos engineering is trying to avoid. And of course, we're all building reliable software already today, right? If you're working at a bank, you want your banking software to work all the time. So what do we currently do? I see a lot of companies who do manual failover tests. So once every 6 months, everyone comes into the office in the weekend, and they move from one data center to the other. Anyone here ever did that or not? Nobody? One? Yeah. A lot of the bigger enterprises who run mission-critical software, they try to do these things. But does that still apply? We're working in a cloud environment nowadays, and we can't fail over from one data center to the other with all our software. We have to be able to do this all the time. So we want to embed this in our DNA. And our software is also becoming more and more complex. So I have these two pictures. Can anyone guess what these are? Yeah, it's actually, this is the Amazon web shop infrastructure diagram, and this is Netflix infrastructure diagram. These diagrams are becoming too hard for people to understand, to read. We can't comprehend with what this does. We know that, and this is only the Amazon web shop. It's not AWS, it's only the actual shop. If you're running applications globally all over the world that have a high load, you want to be able to scale out, and you will get complex scenarios if you plot everything into one picture. Often we don't, because we only work in a certain area. But when we're looking into failures, failures can cascade from one area to the other, and everything can explode if you have built it the wrong way. So in these kinds of scenarios, we're all building distributed applications nowadays. We're all building microservices with different components in the cloud. And if you look at one of these diagrams, you can easily state these complex landscapes. These applications are never fully up. Do you believe that every server in that previous picture will always be up, or the full Amazon website will not work? Well, that's not the case anymore, right? We can't rely on everything being up all the time. So how do we cope with this? We currently have monitoring tools that monitor for CPU usage, memory usage, those kinds of things. Does that still apply? And I think it actually doesn't. If we have 1,000 servers running several microservices, what happens if one server fails, or one pod in a Kubernetes cluster? It shouldn't matter. So these monitoring on CPU usage or memory usage, it's not actually the thing that we want to look for. What we do want to look for is measure what's the impact on our end users. So are our end users still able to do the things they want to do in our web shop or whatever? And how can we measure this? So reliability, it's quite complex to measure. So what is reliability? Is it most people only think about availability. Are all my HTTP calls giving like 200 OK? Well, that's an initial check to have. So, OK, my website's actually responding, but maybe it's responding with, sorry, I can't help you right now. And, well, your user don't have any use of that. Then you have latency, throughput. Are the users actually getting the pages in time, or do they have to wait for a long time? And these can impact users quite a lot. You can actually lose quite a lot of users if your latency or your throughput is not high enough. You can also look for correctness or freshness. Maybe your database is down and you're just showing stuff to your users from cache. Yeah, your website is available, but it's actually showing stuff that's 10 minutes old. Is that still something that users would appreciate or not? So you can build monitoring around these areas. Are my users actually doing the things that they want to do? And if you look at Netflix, they have a really nice monitoring system for this. They call it the Pulse of Netflix, and they have some really good blog posts about that. So I really recommend on reading that. So what they do is they actually measure the amount of streams started per second. Of course, there are millions of subscribers, so during the day they have a constant amount of streams being started. And of course, they have peak times and lower times, but they know what the pattern will be. And what they actually do is, if they see an increase in starts per second, so people are probably pushing the play button all the time, that probably means that something is not working with streams actually starting. And when they see a decrease in starts per minute, then probably the page showing the play button is not rendering correctly. So they really measure user impact, and that's really really useful. So we want to build resilient applications, and we can do that on several different layers. The first one, of course, is infrastructure. Nowadays, we're building our applications in the cloud. It's fairly easy to have our infrastructure in multiple regions, multiple availability zones to, well, have some failover techniques when something is down. We do have to keep in mind, though, that if you're using the same kind of infrastructure, for example, SQL Azure, there could be a bug in SQL Azure worldwide as well. So only different regions will not always help. Then we have the network. Well, as you know, the network is always reliable, unless it's not, which is most of the time. So how do we cope with this? Can we build our networking this way that we can cope with sending messages twice, or messages that will never reach the destination? Next level, of course, your application itself. Can my application work without? Will it work when it's unable to reach the database? Will it work when it does a HTTP call and it gets the wrong response? And the last thing that you should not forget is people. People have a really important role in resiliency and failures. Often when something goes wrong, people still have to intervene, have to do something. Apply a fix, roll out different previous version, etc. But are our people ready to know what they should do in case of failure? And when you're working in an office, you often get fire drills where you learn to, when in case of fire, you all walk out and gather on the parking space. So when the actual fire breaks out, you know what to do. Do your people also know what to do when there's a failure in your application? We need to do fire drills in there as well. And that's where chaos engineering has its place. And failure is inevitable, right? You can't build applications that will never fail, unless you're building applications that have to do with controlling your heart and pacemakers and those kinds of things. Please then do make your software really reliable. But for most cases, most applications, they will fail. And you will have to think about what will actually be the impact of a certain failure. And well, I'll take a Netflix example again, because they really thought through a lot of these scenarios. Think about what would happen in your application if the login mechanism would not work. If the login servers would be down, what would happen? My guess is that most of your application would stop working. You're not able to log in, so you can't do anything. And sometimes this is good, but what Netflix did is that they said, okay, when we can't verify who someone is, maybe just show them, give them the availability to just stream everything. It's only for a little while, and it's our fault that we screwed up the login service. So we will just give them the service for free until we fix our own problems. So the users are not impacted by our fault, and they can still enjoy the service as they are used to. This is really a mindset shift that you have to take, and really have to think about: do we have to cancel the things that our user is doing, or can we just let them do it without logging in or without having certain checks? Of course, if you're doing a bank transactions or those kinds of things, yeah, then logging in is really important. But if it's not those kind of transactions, it's quite often just doable to show them some stuff. And that's what I mean with failing open. If you fail, are there scenarios that you can fail in a way that it doesn't impact users? And if you do fail, can you fail in a certain way that instead of not showing anything at all, can we just give them a little less experience, but still being able to do the most important things? And of course, we test, right? We're all developers. We're all testing our software. But what do we test? When we do unit test, we have a unit, can be a component, can be a class, whatever. What we do test is we have some inputs, and we expect a certain output. What we're testing here is known things, right? We know what the input is, and we know what the output should be. Same for integration tests. It's a bit different, but we have some inputs, send it to one or multiple components, and then we expect a certain output again. That's something that's only testing the knowns. When we're working with failures, we're working with unknowns. And that's really where chaos engineering comes in. And the way I like to explain chaos engineering is actually by seeing it as a sort of vaccination. We're actually applying a little harm into an application and seeing if we can cope with this harm to, in the end, make our application more robust. And yeah, this might sound scary, actually adding some harm into your application. But I think several years ago, people would be scared of actually injecting diseases into your arm as well to make you more immune to these diseases as well. So it's something we need to get used to. But it is, I think it's a practice that we should embrace and should start experimenting with. So what chaos engineering is not, and what I hear a lot by people who heard about Chaos Monkey or those kind of things in the past, it's not just going around in your data center and breaking stuff and seeing what happens. It's not about seeing what happens. You should have an idea of, I should be able to handle this failure, and then see if you actually can do it. Chaos engineering also has an official definition. It's stated on the principles of chaos.org. It's a website where all the people who practice chaos engineering join and created this statement. And what I want to emphasize on is that it's basically the three important areas is doing experiments to build more confidence in your during turbulent conditions. So we want to have confidence when things happen that our application will still survive. And yes, it's comparable to tests, but we call this experiments because we're dealing with unknowns here. In a test, we want to verify that for our knowns, we have a certain outcome. And in chaos experiments, what we do is, it looks like a integration test, but then we enter harm by not sending any response or adding latency in our test to actually see what will happen in the end. So we can do several types of experiments, right? Host failures, where we just kill certain services so they will not respond at all. We could add CPU load or memory usage for certain services to see how they will cope when the CPU of the machine is at 100%. We can add failures in our application, whatever our application just replies with error codes. We can do network attacks where we can increase the latency between different services. And the last one I like to call the brand attack, I don't know who of you read the Phoenix Project. Nobody? A couple of guys did. It's a book about, it's a DevOps book, and in the book there's a guy called Brent, and he's actually the top engineer within the company, and he always knows how to solve every problem, and when there's a problem they always call this guy. What happens if this guy is not there? What if he's on vacation? What if he's hit by a truck? Is your company relying on Brent, or are you able to survive without him? This is often the easiest one to start with. Just give the guy a day off and, well, see what happens. Chaos engineering is also often think, okay, let's break our production environment. And yeah, often we can only test in production because that's the only environment that's like production. There's no place like production. But if you have an acceptance environment that you could run certain experiments on, sure, that's often fine. And that's the problem in this meme is, yeah, you can do it in production, but it doesn't mean you should only do it in production, right? But yeah, production is an area where you should do these experiments. So, how to start this within your company? That's often the case, right? You can't just go to manager. Okay, let's break some stuff in production. Let's break some stuff and see how he responds. But often he will say that it's not a good idea. In chaos engineering, doing these experiments are often done on a game day. They call it a game day. You just get everyone in the office who is involved in having your application up and running, and you start doing experiments with them. And if you're currently already doing DevOps, you currently have probably something like this, is that you will learn from your current failures, right? If you have a certain failure, well, I hope you are able to detect what the failure is. If you know what the failure is, you can fix it, you can learn from it, you can improve, and in the end, when another outage that's similar occurs, you're able to cope with it, and you improved your application. What chaos engineering does is actually the same, but we're not going to wait around until an outage occurs. We're actually going to do this on purpose when everyone is in the office, and not on a Friday night when only the guy on call is there, and well, he has to fix it by himself. No, we do it when everyone is there, so we can fix it all together. And a certain experiment has well, several phases. We always start with a steady state, have an application that's running like normal. Then we define a hypothesis about what could go wrong and what could go wrong that we should be able to withstand. Then we design and execute an experiment around it. We learn from it, we fix it, and in the end, embed it in our organization that we keep doing these kinds of things. First off, steady state. Again, this is about measuring your business metrics. Are my applications running as normal for my end users? Are my end users getting the right results? And these, I showed you the steps with the availability and resilience. If you look at Amazon, for example, it's always a good example because they always have high numbers. They did some tests, and when they increase 100 millisecond load time on their website, they actually lose 1% of sales. And if you know how much sales Amazon does a year, that's quite a lot. That's actually billions. So, what are we going to do? We're going to define a steady state. We have a certain service that we're going to test. And what you could do is, well, for example, this example, we could spin up multiple services next to it, next to the service under test. So this is our server under test. We'll just create 2 more instances of those servers. And we want to route a very small number of users that will go to our service that we will cause chaos on. And we will create another group that's a control group to see if that's responding like normal. And in this experiment service, we can design and execute our experiment. One important part in doing these chaos experiments is you should always be able to roll back and do it fast. So what would happen if there wasn't a database? You can just delete the database, of course, but if that will take hours to restore, you could think of other examples that are far easier to roll back. Hey, we can just create like a firewall rule that disables the application to access our database, which has the same effect as the database not being there, right? So, and those kinds of things are really easy to roll back. So think about those kinds of things. You always want to be able to roll back in case the failure is far worse than you expect. Of course, you might think, oh, well, only this service will stop working, but well, maybe you have some small design flaws and you get cascading failures, and in the end, one small failure will totally destroy your full landscape. So then we define our hypothesis. And how are we going to do this? What you do is you bring in all the people and you start brainstorming what could go wrong. And it's often already a nice exercise to do with the people. So what would happen if the database would not be there? And well, someone from the developer team will say, well, then this and this will happen. And if you actually invite people from the business and those as well, they will say, well, that's not what I expected. You have to get a clear understanding together of what will happen in case of a certain failure. And then you can go over several different problems that you want to investigate. But only investigate the problems you think you have a fix for, right? So, for example, we're running a Kubernetes cluster and we have every application in 3 different nodes. What will happen if we kill a pod? What if we just kill one of those 3 nodes? Our application should still be able to work. If you agree on that statement, everyone together, then you can try and execute this experiment. And it's not someone's fault when this experiment fails, right? If your application was not doing what you expected it to do, it's the group's fault. It's not the fault of the guy that not implemented the retry mechanism the right way, right? You're doing these experiments together, you're responsible together as a group. That's why you do this during a work week when everyone is in the office and you can fix it together as well. If you, I can't emphasize this enough, if you think, well, if we kill the database, then everything will stop working, don't do those experiments, right? There's no use in proving stuff will break. You should only experiment on stuff that you think your application should be able to withstand. So then we start designing and executing our experiment. And my advice is start small, right? I already showed you the picture of the steady state. If you're able to route a small percentage of your users to a different cluster or different part of your application where you can do these experiments on without affecting your full group of users, that's a lot better. So start small. Notify everyone who is involved that you're doing this experiment. So not some other guy who's also watching certain monitors will start running in and or try to fix stuff. And when your experiment is a success, so your application is able to withstand these failures, slowly increase the blast radius. So increase the number of users or make the latency a bit higher to see what are the edges you can actually withstand. And there are several tools you could use to do these experiments. Gremlin is a company, and they actually they sell a product. Well, it's basically chaos as a service, as they like to call it. It's actually, they have a full platform where you just have a SaaS solution where you can start experiments, stop experiments, and well, they have all these little sidecars of scripts that you can add to your virtual machines or Docker containers that can add some harm to them and see what happens. But it's a commercial product. They have a free tier which lets you do some basic experiments. But it's a company created by the people, by a lot of the people who were in chaos engineering for years. They have a lot of people from Amazon and Netflix, where chaos engineering really was born. ChaosToolkit.org is an open source project, and what they try to do is create a common language in which you can define these experiments. So it's really useful. They have drivers towards Azure, Amazon, Kubernetes, those kinds of things to inject harm in there as well. Two other things to mention: the Simian army. Who of you heard about Chaos Monkey? That's probably the most famous well, chaos experiment tool out there. That it's been there for years. And what it does is Chaos Monkey will just go into to Amazon and will just kill random instances there. And Netflix expanded on that, so they have, next to Chaos Monkey, they have Latency Monkey, they have Chaos Gorilla that actually kills full Amazon regions. And they all expanded that into what they call the Simian army. And that's still being updated by them, but it's really, it's quite specific for Netflix. They really embedded this into their Spinnaker CI/CD tooling as well. So it's when certain failures occur, it can automatically roll back using these CI/CD tools as well. So it's really specific for if you're on Amazon and using Spinnaker, those things might still help you. But it's nice stuff to read up upon, because this is a lot of the stuff that started chaos engineering and made it bigger. Then some other small tool, KubeMonkey. That's especially when you're running Kubernetes. Any one of you running Kubernetes? Because it's quite popular. And what this does, it can help you schedule the killing of pods and those kinds of things within a Kubernetes cluster. So after we did our experiments and we're actually able to withstand certain things, we want to learn from it. And what you want to look at was quantifying the results. So yeah, our application was able to withstand this, but how fast were we able to recover? How fast did we detect that something was going on? Did we have auto-scaling when we add some really high load? How fast did that kick in? Those kinds of things you want to learn from when you're doing your experiments. And as I said before, these experiments, you're responsible for it as a group. Don't blame one of the guys for not doing the job. As a group, you came to the conclusion that your application should be able to withstand that, and you're responsible as a whole. Well, then we go into the fix state. Well, fixing is easy, just implement the fix, right? Come up with a solution, fix it so it won't happen in the future. And of course, because you already designed your experiment, you can rerun your experiment to see if the fix that is in place is actually working. And after that, I added the embed phase. If you look up chaos engineering, you will find all these different areas. The embed phase is not in the official document. Well, in the other resources, it's not mentioned. But what I like to do is, when you are doing these experiments, really embed it into the culture of your company. You can use these things for onboarding new people. When you're onboarding new operations personnel, you can really use these kind of experiments to train them to do these fire drills in case of emergency. What will happen? And you can also add continuous chaos. And what continuous chaos does is, if you have certain experiments like, okay, we're always deploying our application to at least 3 nodes. So when something happens, the other 2 will take over. What you could do is, okay, well, so every hour we will just kill one of the nodes and see what happens. Netflix is actually doing this, and they're running over 1,500 chaos experiments a day in an automated fashion. So they actually are this far that they're on an opt-out method. So when you want to deploy an application, there's actually if you don't do anything, the script will actually start killing your nodes unless you opt out of it because you say you're not ready yet. But if you really embed this into your culture, and you know that these failures will happen, because they happen to all of us. But if you're prepared for it, then it really helps in the quality of your application. So really embed it into your culture that failure will always happen. So that's basically chaos engineering. And what's really close to chaos engineering is actually building your application this way, so it actually should be able to withstand lots of these failures. So what I would like to wrap up with is call out a number of architecture patterns that will really help you build more resilient applications. Well, the first one is quite obvious. It's just running stuff in parallel, right? If you use something that has an SLA of 99%, you might think, well, 99%, that's quite good. That still means that that service can be down for 3 days and 16 hours a year. That's also quite a lot. So often when I talk to business people, they say, well, 99% seems reasonable. Then I say, okay, so this service will be down 3 days in a year. I was like, oh, okay, then 99% is not high enough. What you could do is have 2 instances in parallel. Theoretically, you could multiply your availability and go to 99.99, which means you only have 53 minutes of downtime. When you have 3 instances, you could multiply these again, and you can go to 6 nines, which results into 32 seconds downtime a year, which is, well, fairly reasonable. A side note, though, is, are these really separate things? If you're just running 3 instances of the same cloud component, is that cloud component never down across regions? Is it never down across availability zones? If SQL Azure is down all over the world, it doesn't help that you have one in Europe and one in the US. But if you have a SQL database and you have some other kind of database as a failover strategy, or you have some caching in place, then you can really think about these kind of numbers. Then async communication. it was already mentioned in the microservice talk that was just before here. If you have asynchronous communication, it's a lot easier to do retries. You need a lot less connections per request, because you just do a request and you don't wait until the answer. You just do a post, and sometime you will get a result back. This scales far. It's a lot easier to scale compared to synchronous communication. So if you really focus on messages instead of doing synchronous calls between services, it really helps you in reliability. And of course, decoupling the different services. If one service should be down, you don't want to have cascading failure over to all of your other services. And use things like publish, subscribe, or listener patterns to decouple all of your services. That should not be there. Then we have queue-based load distribution, which really is really connected to this asynchronous communication. If you have a database and we have several different instances which are all talking to the database, well, this database might have a hard time with all these different connections, especially when they all do like long queries or those kinds of things. It can't handle all of those connections at the same time. What you could do is move it to a more asynchronous manner and have all these services push a message on the bus. And on the other way, we just have one processor or as much processors as you can handle, which handle all these messages in an asynchronous manner. Then we have idempotent APIs. So we already discussed the network sucks, right? It's not reliable. So if we're doing asynchronous communication, how bad is it if we do multiple messages that are actually the same? And building idempotent APIs helps us to do the same message over and over again without having different results. And it's really important to keep in mind what kind of HTTP calls can I do. If you use a lot of post and patch, those kind of things are not idempotent. So if I do a post and I do a post again, my data will be different than when I do two puts in similar order, right? So looking for idempotency really helps you in decoupling these services again. Then we have the bulkhead pattern, which actually comes from the bulk within a ship. And that's actually compartizing your application in different silos. If one breaks, not your full application should break. You could think about these examples like, again, if you're running a Kubernetes cluster, have a certain service, set a certain cap on the memory and CPU it can use. So if 3 services are running on the same machine, and one service starts using 100% CPU, not all the other services are affected by it, right? So if they all have their own isolated area, then these services will not affect each other. And the same works within a ship. If the ship is hit in the hull, it will only flood that part of the ship, and the rest of the ship will still stay afloat. Then we have the circuit breaker, right? We all know this from our homes. When certain things go wrong for a certain time, we just want to stop doing it, right? If we keep querying the database and the database is not responding, maybe after a while we should stop hammering the database, because the database already trying to get up, but it's being hammered by all these calls and all these retries again. So what a circuit breaker does is after certain failures, certain amount of failures, stop doing the calls to the database and start using the cache. Or you can add certain retry mechanisms. If you're using .NET, Poly is a library that can help you doing these things. And when you do retries, please add stuff like jitter. So instead of, okay, when my connection to the database does not work, we're first going to wait. You have exponential backup. So first we're going to wait for 1 second, then 2 seconds, then 4, then 10. This still hammers the database in certain amounts of times because everyone is waiting the same amount of time. If it's not there, then okay, it will wait 5 seconds and then boom, then hammer the database all at the same time. When you add some random jitter, so wait 1 plus X seconds, you will get a far more distributed load on your database, making it easier to get up again. Then we have things in our software architecture where we can split responsibilities, right? A lot of people who are building microservices are hopefully doing this by splitting responsibilities for read and write, right? Like things like CQRS. If you build these things, you can also scale differently, right? Maybe the amount of writes to a database is often far less than the amount of reads, right? And we can have a read database that's really expanded globally and can handle far more load than the database that we are actually writing to. And this gives us, again, far more flexibility in what our application should handle. We shouldn't be stopping the writes to our database because we have too much reads. If we split this up, we can scale this separately as well. So seeing we're almost out of time, I want to wrap up. Want to give you 2 key takeaways. First of all, doing chaos engineering is a big cultural shift. So really talk to your managers, try to do these experiments, and I think you should really adopt like full cycle developers, so where you can, as a developer, you're really responsible from the start to the end. And the next thing is just start doing experiments, really small scale and acceptance if it's possible, and just expand it from there, learn from there. So with that, I want to end, and I want to end with this famous quote by Nora Jones, which is one of the writers of the chaos engineering book. And her quote is, chaos engineering doesn't cause problems, it merely reveals them. So with that, I want to thank you and enjoy the beers.